Okay, so in this video, we will answer the following question. Does the improper integral I converge or diverge? And of course, we will use the idea of the comparison theorem. So the integral is of 1 over ln of x from 1 to 2. And as we'll see, this is a rather subtle question, but we'll use something that we haven't used in a while, namely the idea of the tangent line to a curve. And this will be the key in answering this question. So let's look at the graph of ln of x, specifically between x equals 1 and x equals 2. At the same time, we'll understand why this is an improper integral of type 2, as it clearly is not of type 1, as we have finite bounds of integration. So let's see. And ln of 1 is exactly 0, and above 1 ln is positive, and we are considering 1 over ln of x from 1 to 2. And you can see now why the integral is improper. Between 1 and 2, ln is perfectly defined and continuous, but every time you have the ratio of two functions, you have to be wary of a division by 0. And between 1 and 2, ln is equal to 0 at 1, and so at 1, at the lower bound of integration, we have 1 over ln of 1, which is 1 over 0. So we have a division by 0, therefore a vertical asymptote. So again, clearly now, we see that we have an improper integral of type 2. Now how do we go about this problem? The idea is, once you see it, very simple, but at the same time very subtle, is to consider quite simply the tangent line to the function y equals ln of x at the point x equals 1. So if you look at this tangent line, you will find quite simply, and I will leave the calculations up to you, this is something that's quite easy, that the equation is y equals x minus 1. And this is our tangent line. Specifically to the function ln of x at x equals 1. And you can do a quick check, right? The slope of the tangent line is supposed to be the derivative of the function at the point. The derivative of ln of x is 1 over x, 1 over 1 is 1, our slope is 1, check. And the tangent line is supposed to pass through the curve at that point, the point being x equals 1, y equals 0. Well, when x is 1, 1 minus 1 is 0, so indeed this is the right tangent line to the curve at x equals 1. And now we can make a very simple but key observation in this problem. Because ln of x is concave down, we can clearly see in the picture that from 1 to 2, the tangent line lies above the actual curve ln of x. And so x minus 1 is bigger than ln of x. Equal to at 1, as long as x is between 1 and 2. And again, we're only interested in this range, so we don't care anywhere else. Actually, it's true everywhere else, but we don't care about this, specifically for us between 1 and 2. And now, the other key fact is that ln between 1 and 2 is always positive and 0 at 1. So if we invert both, this will flip the inequality. So if x minus 1 is bigger than ln of x, 1 over x minus 1 will be smaller than 1 over ln of x. Again, if you divide by something bigger, you get something smaller. And so now we are essentially ready to go. This is our f of x, the original function. And now we have a much simpler and slightly smaller function in 1 over x minus 1. This is our g of x. So again, we'll ignore the original integral, and let's see what happens if we integrate g from 1 to 2. Well, we have to be careful as we have again an improper integral on our hands. If you look up the function 1 over x minus 1, it is a rational function, but at 1, at the left-hand point, we have a division by 0, therefore an infinite discontinuity. So as always, we have to first avoid the discontinuity. And 1 here is the only such discontinuity. And then we have to let t approach 1, but of course from the right. If you look at a picture of the interval, right, this is from 1 to 2. 1's the problem, so we avoid 1, but t must be slightly larger than 1, so t must approach 1 from the right. And now we're ready to go. From t to 2, as t is slightly larger than 1, we avoid the discontinuity at 1, and now our function is continuous over a finite interval, and so we can use here the fundamental theorem of calculus. And again, we have essentially a trivial integral. The antiderivative of 1 over x minus 1 is the ln of x minus 1 in absolute value, which we must evaluate from t to 2. Well, at 2, let's see what we have. The ln of 2 minus 1, that's the ln of 1, which is 0, gone, minus the ln of, replacing x by t, t minus 1 in absolute value. Well, what is this limit? Let's look back at the graph of ln. As t approaches 1, t minus 1 will approach 0. 1 minus 1 is 0. We have here the absolute value, so it's clearly going to be positive. So it's 0 plus. And as the argument approaches 0 from the right, we can see the ln function goes to negative infinity. But we have negative of that, so the limit is simply positive infinity. As I've just said, the ln, as the argument approaches 0, the ln approaches negative infinity. And we have the negative of that, and so this integral blows up. Well, we're essentially done now because we'll compare the initial improper integral to this new improper integral, and we'll see that the initial one will also blow up. So we have the integral from 1 to 2 of 1 over ln of x dx. But 1 over ln of x is bigger than 1 over x minus 1, so its integral is larger as well. And we've just found that this integral is actually infinite. And so we now have our conclusion. The initial improper integral must be at least as big as infinity, therefore it must be infinite as well. That is the only option. And so the improper integral I diverges. And recall that this was what we called I. the original improper integral. So it blows up. And we're done. But you have to appreciate here the beauty and the subtlety of the solution. Once we think of comparing the function with its tangent line, then we have the very nice and simple inequality, and then the problem becomes actually very straightforward. But if you don't think of using the tangent line, you're going to have a hell of a time here. So a beautiful example of how we can use the idea of a tangent line to a function in a particular example of determining whether an improper integral converges or diverges. So just a beautiful application of the tangent line.